Hello guys, today I'm going to explain you how can we solve this problem possible by partitioning. This is another problem from Leetcode's May challenge. The problem statement says that we are given a set of n people, those are numbered from 1 to n, and we would like to split these people into two different group of any size. So there is a relation given, like a dislike relation given, and this tuple denotes that one does not like 2 and also 2 does not like 1. Similarly here it says 1 does not like 3 and 3 does not like 1. Similarly this one. So we need to know whether we can divide them in a group such that any person within one particular group does not have someone whom he does not like.
So if we take this example, the first example where this relation is given, and if we consider this as a graph based problem where an edge represents that the nodes dislike each other, so what are we supposed to do? We are supposed to break this graph into two different groups such that no two neighbors should be in the same group. In another statement we can also say that can we color this graph in using only two colors so that no two neighboring nodes should have the same color. One color represents a group. Let's say if we color this one as red, and then we should not be coloring this and this one as red, and then we can color this one as red, and now we can choose a second color to color these two. If we can do this for like if our graph can follow this particular rule that all its nodes do not have the same color as its neighboring nodes, so we can say that yes, this can be divided into two such groups, otherwise it cannot be. Let's take another example where this cannot be done. So if we consider this particular graph where whatever we choose, whatever we do, we will never be able to color these two graphs in using two colors, so that the neighboring, for each node the neighboring nodes are of different color. So let's say for example if we color this one with green, and then we have to choose two different colors for its neighboring nodes. So if we choose red for this one and red for this one, then this relation is going to violate our rule that these two are basically are also adjacent nodes and they are of the same color. Similarly, if we would have tried to color this one with the red first, and if we try to do this one with green and this one green, then ultimately these two would have the same color, and again this violates our rule. So this cannot be done. So in this case, yeah, as we seen, this graph can be divided into two such groups, and this one cannot be divided into two such group. So one can consider that if a graph contains a cycle, then it can never be divided into two such groups, but that's not always the case. Let's for now consider this particular example. Here the graph has a cycle, but we can still make this as like we can still divide this, because we can color this one and this one with the green, and these two nodes with the red color, and vice versa. We could have tried to color these two as green, and then we could have tried to color these two as green one. So this contains a cycle, but still it can be divided into two such groups there where all the nodes do not have any other node whom they are disliking. So let's see how we can solve this problem.
So the simplest approach here is to start with any node and do a BFS along with this node, starting from this node. And in BFS what we are going to do is we are going to maintain a level, like the current, we can assume that the current node is at level 1 and all the directly adjacent cells are at or adjacent nodes are at level 2, and then further ones are at level 3 and 4 and so on. So yeah, I mean this one would also be at level 3 because it's adjacent, directly adjacent to node with a distance of 2 or a level of 2. So we are going to pick one level, all the nodes at one level, and we are going to give them a different color than their parent node. So for example, in
In this case we could simply give this color as this node as color red, and let me just use a different element here. So if this one is marked as red, we are going to push this one into, and we are going to push its adjacent element into the queue. So we will push 2 and 3 into queue. So now once this level all the nodes at this level is processed, we are going to change the color to green, and we will take the first element out of the queue. So we will pop this one out, and we will mark this one. We will first compare it if it is already colored or not. Because this is not colored, so we are going to give this particular node a different color. So we will give this one with the color green, and then the next element, but before checking the next element in the queue, we are going to check all its adjacent nodes. So its adjacent node is this one, which is already processed, and this one, which is 5, this is not processed. So we are going to push this one into our queue, and let's push this particular node into queue. And then we have the next element from queue, which we will pick and process. So this one is also same as 2. This does not have any color till now, and its adjacent nodes are only 2 nodes. First one is already processed, so we will not check that one. And the next one is its child, which is 4. So we'll mark this one as green, and we'll put 4 into our queue. These 2 nodes are also processed. So what are we going to do is we are going to go for the next level, and so we will change our color to red now. So let's pop out the first element out, first element from the front. That means cross this 5 out, that and then we will check whether it is already processed or not. So it's not processed, and so we will check its child element, which is 4, its adjacent element. 2 is already processed, and we will mark this one as red, and we will push this 4 into our queue. Let's just for now push 4 here, and then we'll go to the next element from our queue, and we mark this as processed. We'll come to 4. We will pop this one out, and then we check what's its color. Its color is it is not marked any color. So we can just give it a red color, and then we will check its adjacent cells. So we can see that there is an adjacent cell here, which is already marked, as well as it is marked with the same color as of this particular node. So we see a violation in our rules, so we can simply return false from here. So what if there was no relation between 5 and 4, like there is no such edge between them? So in that case we would not have 4 here, because this 4 in the queue came from this relation. So we would simply remove this one, and then when we will process 4, we will simply see that there is only one element which was adjacent to 4, and this is marked differently. This is colored differently, so we don't see any violation, and we were able to give colors to all the graph. So once we have processed all of them, we can simply return true in the end. One thing to keep in mind here is that we should not only stop once we have processed all the nodes by doing a BFS from a particular start node. In this case we started our BFS from node 1, but there can be a chance that this graph was disconnected, and we had another graph here which had like 6, 7 and 8, and they had the cycle. So we cannot divide this overall graph into 2 such group, because this particular group cannot be divided. So what I am saying here is that we should not only stop doing the BFS once we have seen one BFS successfully completing its graph coloring. We should try to do the graph coloring on all the uncolored nodes as well. So for doing that, we can just maintain an array of, let's say for example here we can maintain the array of 8 elements, and initially we can mark all those elements as 0, like uncolored, and then we can start giving color to both to all the nodes, and try to see if they are violating the rule or not. So I guess that's enough with the explanation. Now let's jump into the code and see how we can implement this. So yeah, as you can see, I have already implemented this. I'm maintaining a list of coloring colors for each node, which are initially marked as 0. That means they are uncolored, and also maintaining an adjacency list as a bidirectional edge between two nodes. Also, I have a queue to do a BFS, and to do a BFS as a level order traversal. What I'm doing here is I'm just first finding the first uncolored node. Like if a like if a node is already colored, then we will not consider this. In this case is especially to consider disconnected graph. And then we are finding the first uncolored node, and then we'll push it into the queue and then do a level order traversal. So as I've said, I'm alternatively changing the color at each level. So this is being this color is changed for the next level, and then I'll pop out the first element. I mean pop out all the elements at this particular level, like until I have seen this size is telling the number of nodes at the current level. So I'll keep popping out all the nodes until I have finished processing for all the nodes at this level. So I'll give the color to node. I'll give the same color to all the nodes at a one particular level, and then I'll check for each neighboring nodes of this current node that if their color are same as the current node, like the neighboring cell are also processed and they have the same color as the current node, then we can return false. And if we are able to do the coloring for all the nodes in the graph, whether this is connected or disconnected, then we can in the end mark this as successful graph coloring, and we can return true, saying that we are able to divide this given group into two different groups. So yeah, that's all. I hope you were able to understand, and thanks for watching this video, guys. Please hit the like and subscribe button if you like my work.